In our previous lectures, we explored three forms of induction principle. So let me state all these forms. The first one was our most well-known mathematical induction principle. For every property of naturals, for every predicate phi over naturals, if phi holds for 0, if 0 satisfies this property, and if this property phi may be translated from n to n plus 1 for whatever n, given these two are true, we are allowed to conclude that phi holds for every natural number. Another form was the least number principle. It is something else. It is not about universal properties, but about something that exists. For every property phi, if there is a number n, for which, or let's better call it m, if phi holds for some m, at least one m, if phi is not universally false, if it is true at least sometimes, then there is a number n, which is the minimal number for which phi holds. It is the least number with that property. There exists such n that phi of n holds, but for every number which is less than n, phi fails. Phi is not true for all the numbers less than n. So we have something like that. Say 0, n, here we have phi at n. We don't know whether it is true at n plus 1 or anywhere else, but here up to n minus 1, this is false. Here we have no phi. This is the main idea. So phi is the least number at which phi holds. And the last form of this principle was the so-called strong induction principle, which says that if whenever phi is progressive, then phi holds for every natural number. The conclusion is the same as we had in the regular mathematical induction principle. But what does it mean? Progressive. Progressiveness is like these two combined. Progressiveness is a form of inductive step, which in fact contains also the base case. So progressiveness is just that. For every n, it is enough for phi to hold for n that phi holds for every lesser number, for every m which is less than n. So given phi holds for all numbers less than n, phi is necessarily true for n itself. Is this idea clear? It is counterproductive to post anything to our chat for I have no means to read it. I see you are not posting anything. Just switch your microphone on and speak. There is no need to raise your hand. Okay.
I have a question.
Okay, thank you. So please.
How do we know which method we should use for some cases? How do we know when?
What is better? It depends on your problem. But logically, they are equivalent. And our goal today is to prove this fact. Practically, you can use whatever principle which you think fits your problem better. For example, most likely, you want strong induction when you make a reference to some numbers which are not directly precedent to our n. So if you want to prove something for n, you may need this for, say, n divided by 2, n over 2, not just n minus 1. In this case, most likely you want strong induction. You naturally apply the least number principle when you want to prove that okay, you most likely you will apply it in a contrapositive setting. So you want to prove that there is no you want to prove that every n satisfies phi. Assume that it is not the case. Then take the least possible n which doesn't satisfy phi, and then obtain a contradiction. In fact, we saw at least 3 examples. One example for every principle. But of course, as these principles are logically equivalent to each other, there is no hard rule here. Try whatever works, and with practice you shall see what is more convenient. So our theorem for today, theorem 1, and maybe only theorem, is as follows. These statements are logically equivalent. Of course, you may wonder that if they are all true, they are logically equivalent. But why do we know that they are all true? We can take one as an axiom. But what about the other principles? We can either prove it not using the principle itself, just taking one of this as an axiom and deriving the other one without any recourse to induction. So the main idea here is as follows. What should we take as an axiom? And I'll prove that it doesn't matter. Every one of these principles is, so they are equally good. They're equally good. You can take one and derive the 2 remaining principles, not using any induction, anything except your basic axioms. Okay, our theorem 1 is as follows. 1, let us state it the following way. One can prove without induction. It is important, for otherwise you can use induction to prove induction. So you can use, say, the least number principle to prove it. That's not good. One can prove without induction that the following statements are pairwise equivalent. That is, if one is true, then the other one is true as well. the strong induction principle, the least number principle, and the mathematical induction principle. So one can obtain one principle from any other one. How should I argue technically? I'll prove three implications. I'll prove that from the first principle you may obtain the second one. From the second one you may obtain the third one. And from the third one you may get the first one. Of course it is enough, because given these three implications, it is easy to obtain, say, strong induction from least number principle. Okay. Assume the least number principle, then by this implication MIP is true, and by this implication SIP is true as well. Is it clear?
Yes.
So we have to prove three implications. Let's do it without any haste. We shall give a detailed proof. From 1 it follows 2. What is given? What is given? The strong induction principle is given. Let me rewrite it here, reproduce the statement. For every psi, I shall change the letter for technical reasons. Clearly, this letter is bound by the quantifier, so it doesn't matter whether I call it psi or phi. So for every psi, like in psychology, they pronounce it psi. For every psi, if our progressiveness statement for psi holds true, if this one is true, then for every n, psi of n is true. And what is required? It is required to prove the least number principle. So I have to prove that for every phi, something holds. But how can I do it? I can just take some particular phi, take some arbitrary phi, and prove that if phi holds for n, then for m, there exists some n for which phi holds as well, but for every number which is less than n, phi fails. Is it clear?
Yes.
Look, what is given? Something abstract, something high level. It is given that for every property, something holds. So the choice of this property, psi, to which to apply this strong induction principle, is mine. So I can choose psi. It is guaranteed that for every psi it will work. So let us take not phi for psi. Phi means psi. Let psi mean not phi. That phi is not true. Psi says phi is false. Is it clear?
Yes.
We can take whatever property for psi. Some phi was given. Now let us take not phi. It is not the case that phi for psi. Aha! And now we shall do a series of tricks of some logical transformations. Aha! So then I have this one, but for our particular psi. Okay, let me rewrite. For every n, if for every m less than n, psi of m holds, read not phi of m, then phi is false for n. And this is enough for every n, not phi of n. Do you agree? Interesting. And now look, let's do some logical transformations. We know that A implies B is logically equivalent to not B implies not A. Do you remember? You can check it using a truth table. When is this one false? This one is false if and only if 1 takes A takes 1, but 0 takes but B takes 0. And when this one is false, when not B takes 1, that is B takes 0, and not A takes 0, that is A takes 1. They are equivalent, they are false simultaneously, hence they are true simultaneously as well. Is it clear?
Yes.
Yes.
So we can rewrite it in the following form. So let this one be B and this one be A. So what do we have? This is equivalent to not B, that is, it is not the case that for every n not phi of n holds, then it is not the case that. And now I'm simply rewriting this stuff. Nothing creative, nothing interesting here. Aha! But now I can do some quantifier logic. It is not the case that all x satisfy A. What does it mean? This is logically equivalent to what?
There exists.
There exists x for which A fails. According to that, I can rewrite this thing. So there exists n such that not phi of n. But double negation can be cancelled out. Okay, let's do it a little bit later. But what do we have here? The same. There exists n such that our implication, here we have an implication, our implication is not true. Do you agree so far?
Yes.
Look, the structure of our formula has got closer to what we require. If there exists, then there exists. I'm doing purely formal transformations. No fantasy, no imagination here. No particular content, no intuition about numbers, figures, I don't know, triangles, real valued functions, whatever. Pure logical transformations. Aha. What else? double negation can be cancelled. Do you agree? Not A is logically equivalent to A. Ladies and gentlemen, isn't it obvious? Aha, so here I have, there exists n which satisfies phi. Okay. But here I have a negated implication. Please tell me, when an implication is false, when it is not the case that A implies B. When A doesn't imply B, according to the truth table. Is it that hard to comprehend?
When A is 1 and B is 0?
Of course, but in terms of logical equivalence, that means that A is false, A is true, but B is false. So this formula is equivalent to A and not B. Do you agree? They are equivalent. That means that they have the same truth tables.
Yes.
Okay. So here I have, under the quantifier, there exists n such that this part, the assumption holds for every m less than n, not phi of m. Aha. This holds, but this one is false. Some cosmetic steps. Here I have a bound variable. It doesn't matter what its name is. I can rename it to m. Why not? Why not? There exists something that satisfies phi. I can call it m. And here I can do the following. First of all, I want to get rid of double negation. So here I have phi of n, and for every m less than n, not phi of m. Ha! What is it? What is it? Look. This is identical to what we require. It is identical. It is exactly our least number principle. Isn't it clear?
Yes.
So, what have we done? We take the strong induction principle and applied it to a particular property, namely not phi. So this procedure, it is similar to a proof from the contrary. So we have assumed, we have considered not phi instead of phi. We have applied the strong induction to not phi, and we have obtained by the way of logical equivalent transformations our least number principle. Was it clear? Or do you have any questions? I have a question for you. Have we used any induction here? Have we proved anything by induction? Of course, we applied this principle, the strong induction principle, of course, but this was explicit in our assumptions. But have we used induction as a method of proof? No. We have done a sequence of logical transformations. No induction. No induction. So this implication from 1 to 2 doesn't depend on any induction axiom. Of course, the assumption of this implication was an induction axiom, but in the course of proving this implication, we have used no induction. Is this idea clear? I will be happy if at least some of you really understand this argument. And of course, I will be glad to answer your questions if you have any. Ladies and gentlemen, it is abstract, but it is not complicated. The only problem here is that it is all abstract. So you have posted something to our chat. It's clear. Okay, that's very nice. Okay, let us continue. We have two more implications to prove. From the second to the third one. Here we shall do the same trick. We shall replace our predicate phi by, we shall replace it with the negation of phi. What is given now? The least number principle. What is given? The least number principle is given. Let me reproduce that. Here it is, by the way. If there exists M, excuse me. Let me reproduce it, but I'll rename phi to psi. For every psi, if psi holds somewhere for at least one number, then there is the least number n with this property. There exists n such that psi of n, but for every lesser number, psi fails. That is given. What is required? The mathematical induction principle is required. So for every phi, I have that phi of 0 and this inductive step are enough to obtain for each n phi of n. Okay, let us take some arbitrary phi and prove all what remains. So let us take some arbitrary phi and prove this implication. If phi of 0 and if phi of 0 and for every n, phi of n implies phi of n plus 1, then for every n, phi of n. Aha! So now I am expected to prove an implication. But how can I prove one? In order to prove an implication, I may assume that these things are true. Let's do that. Assume that indeed phi of 0 holds. It is given that phi of 0 holds. It is given that phi of n implies phi of n plus 1. Assume that these things are given. And we are interested in proving that for every n, phi of n holds. Was this transformation clear? I have just assumed that our assumption was true.
Yes.
How can I prove it? Of course, I can take some arbitrary n and try to prove. But there is no obvious way to do so. What is n? How great it is? I don't know that. I don't know that. So I'd better prove it indirectly, namely from the contrary. I will assume for the sake of contradiction that it is not the case that for every n, phi of n holds. And given this assumption, now it suffices to get a contradiction. Is this idea clear? I'm reasoning from the contrary. I have assumed that no, it is not the case that phi holds for every n. So it is enough to take this assumption to absurd, to lead it to a contradiction. Do you agree? Any ideas? So apparently you are. Okay. If one is to believe these reactions, thumbs up and so on. Okay. So I will continue. Okay. But what does it mean that it is not the case that phi of n holds for every n? What does it mean? What does it mean?
There's this one case that
Yes, there exists some n. Let's call it, say, n0, or as an American would say, n naught. Or let's better call it n0. There exists n0 for which phi fails. There exists some n0 with this property. And now we shall apply the least number principle. Let psi be not phi. Then, according to this least number principle, from this assumption, which we are given with, we have the following. If not phi holds for at least one number, then there exists n such that not phi holds for this n, but for every lesser number, not phi fails. So this is true. This one is true. This implication is true by assumption. So that is true. And this is also true. We have a situation of the modus ponens rule. A implies B is true. We have seen it for many times. A implies B. This is true. A is true itself. What is the natural conclusion? What is true then? What is true? I haven't got it. Have anybody? then B is true, of course. We have a true implication with a true assumption. Clearly it is true. This equivalent, it says that there is something. The name doesn't matter. There is something which for which phi fails. And we know that if there is something for which phi fails, then this part, this conclusion must be true. So there exists n such that not phi of n, but for every m less than n, not phi, that is just phi of m, holds. Is it clear?
Yes.
So now we shall analyze this n. Consider this n. Let us take this number. It is a natural number. But what is it? There are two cases, at least. The first case is as follows. N equals 0. But we know that phi fails for n. So phi must fail for 0. But what do we have here? So we have our base case, BC, that is for base case, and we have our inductive step, say, IS. Let's call it so, I mean. By the base case, not BS. BS is bullshit, but BC is base case. By the base case, we have phi of 0. But these two are inconsistent. We have got a contradiction. But anyway, we are seeking for a contradiction. We have got what we want. Is it clear?
Yes.
Yes.
Now let us consider case 2. Now n is not 0. N is something like m plus 1. You know, for every natural number, it is either 0 or of the form m plus 1. So n is m plus something. But now this m is clearly less than m plus 1. It is less than n. But I know that for every number which is less than n, phi holds. Therefore, phi holds for our m. Okay. But by the inductive step, here it is, I know that if phi holds for whatever number, it holds for the next number as well. So by the inductive step, I have phi of m plus 1. Is it clear?
Yes.
The inductive step guarantees that if it holds for whatever number, for, I don't know, however you call it, n, m, whatever, for every number, if it holds for it, then phi must hold for the next number, for its successor. But if I have, as I have that phi holds for m, then I have that phi holds for m plus 1 as well. Is it clear? Ladies and gentlemen.
Yes.
Okay. Ha! But n equals m plus 1. And I know that phi fails for n. So I have that phi fails for m plus 1. Phi fails for m plus 1, but phi holds for m plus 1. The only possible consequence of this two is a contradiction. So I have obtained a contradiction in both of these possible cases, when n equals 0 and when n is not 0, when n is something plus 1. Both these cases result in a contradiction. So, having assumed phi of 0, the base case, and the inductive step, I have let the assumption that phi of n fails somewhere, that it is not the case that phi of n is true everywhere. I have led these assumptions to a contradiction. Hence, assuming all the other things, I must necessarily conclude that phi holds for every n. Is it clear? Okay. That is enough for these two implications, from 1 to 2 and from 2 to 3. Please notice that in both these cases, we have changed phi to, it is not the case that phi, to not phi. Because this least number principle is, one may say that it is a contrapositive form of induction. And practically, this boils down to the fact that you generally need an argument from the contrary. When you're proving something by induction in the form of the least number principle, assume that it is not the case. Assume that for some n, phi fails. Let us take the least such n. So this transformation to not phi, this move from phi to not phi was the consequence of this fact that you generally need to reason from the contrary when applying the least number principle. Okay. The only implication which is still to be proved is from 3 to 1. And this one is the trickiest. This requires a little creativity, a little imagination. So we're interested in proving that the strong induction principle, or excuse me, that our mathematical induction principle, number 3, entails the strong induction principle. So what is given? The mathematical induction principle is given. For every psi, if psi holds for 0, and for each n, psi of n is enough to obtain psi of n plus 1. So the base case, the step. So if these two are in place, then we have psi of n for every number n. This is assumed. And what is required? The mathematical, the strong induction principle is required. That is, for every phi, if phi is progressive, that is, in order to obtain phi of n, it is enough, it suffices to have phi for all the lesser numbers. If this is given, then phi holds everywhere for every natural number. Okay. Interesting. Okay, let us try proving that. First of all, let us take some arbitrary phi and then erase this quantifier in this required part. Now, I want to prove an implication. Routinely, in order to prove an implication, I may assume that its assumption is true. If its assumption is false, of course, there is nothing to prove. From a false assumption, it follows everything. Assume that it is true. So now, the only thing that remains to be proved is this one. For every n, phi of n. For every n, phi of n. By the way, notice that this statement is exactly what we called progressiveness of phi. It says that phi is progressive. Is it clear so far?
Yes.
Okay. And now this little bit of creativity we need here. We should take something interesting for psi. It is not phi. You know, here we have for every n psi of n, and here we need for every n phi of n. For psi, we need something stronger than phi. You know, we are going to apply mathematical induction to prove strong induction. The key is to apply mathematical induction to a stronger statement. And our statement will be as follows. Let psi of n be just that. This, say, conjunction. Phi holds for 0, phi holds for 1, phi holds for 2, for all numbers which are less than, please notice, strictly less than n. Or, more precisely, it is this quantified statement. For every m less than n, phi of m holds. This is our psi. So my task is to prove. Let us apply the mathematical induction principle to our psi. Let's prove for every n psi of n by induction. In order to do so, I need, of course, the base case and the step. So the base. Why do we have that psi of 0 holds? It's quite clear. In fact, we already proved it. What is psi of 0, first of all? Psi of 0 is this statement. For every m which is less than 0, phi of m holds. That is, for every m, if m is less than 0, then phi of m holds. Do you know any natural number less than 0?
No.
No, exactly. So that means that this statement, this assumption is false. But from falsity, it follows everything. Hence, this whole implication is true. The entire implication is true. So this thing is true. Psi of 0 is true. Is it clear?
Yes.
Okay. Now we need the step. This step. What is this step? I need to prove the following. For every n, if psi of n, then psi of n plus 1. So far, I haven't used this assumption that phi was progressive, but here I will need it. Okay, I am going to prove this thing, and then I will apply mathematical induction. Okay. What is given for this step? Assume that some n is given and psi of n is given. What is required? It is required to prove psi of n plus 1. Let us rewrite both these statements. What is psi of n? Psi of n means that for every m which is less than n, phi holds. And this says that for every m which is less than n plus 1, phi of m holds. Do you agree? Do you agree with that?
Yes.
So you do. Okay. Look here. I want to prove this thing. That is, for every m less than n plus 1, something holds. Okay. Let us take some m and assume that it is indeed less than n plus 1. So let us add this m to what is given, and also assume that m is indeed less than n plus 1. With this new assumption, it suffices to prove phi of m. Is it clear?
Yes, sir.
Okay, ladies and gentlemen, we know that m is less than n plus 1. How is it possible? Oh, look. Here is our natural number series. 0, 1, 2, and so on. Somewhere here we have n and n plus 1. Which numbers are less than n plus 1? These are all numbers which are less than n plus n itself. Is this idea clear? What is less than n plus 1? All the numbers which are less than n plus n itself. Do you agree?
Yes.
So we have two cases. The first case, I know that m is less than n plus 1. The first case is when m is less than n. Ha! But in this case, I have already known that phi of m holds. It holds for every number less than n. M is less than n, so phi of m. That's all. We are done here. The second case, is trickier. In the second case, m equals n. Okay? M equals n. But still, for every number, I know that phi is progressive. I know that phi was progressive. So phi was progressive. Here it is. We have it assumed. Phi was progressive. Aha! What does it mean? That means that if for every m which is less than phi of m, of course it will be better to call it not m but some k, but it doesn't matter. By progressiveness, this is enough to obtain phi of n. But this is true. This is true. By assumption here. This is true. So what is the result? So phi of n holds. But our m was just n. We have obtained phi of m in this case as well. Is it clear? So this step is done. The base is done. So I can apply the mathematical induction principle to psi. Why can I? Why may I apply it? Because it is given. It is given as one of my assumptions. I have everything in place now. Psi of 0 and this step. So, by the mathematical induction principle for psi, I have for every n psi of n. But my ultimate goal was not psi of n, but phi of n. But what is psi of n? Psi of n means that for every m, for every n, for every m less than n, phi of m holds. The only remaining question is whether it is enough to say that phi holds for every number. Let's rename it to k. Why phi holds everywhere? Given for every n, for every number less than n, phi of m holds. Okay. Let me prove it. Consider an arbitrary k. Let us take whatever k. Whatever k. We need something which is greater than k. Now let n be k plus 1 and m be just k. So what do we have from here? For every n, so including k plus 1. So for every m which is less than k plus 1, phi of m holds. But clearly, k is less than k plus 1. Then phi of k holds as well. So I have taken an arbitrary k and proved phi of k. So we are done here. Everything is okay. Is it clear?
Yes.
So what have I done here? I have strengthened the statement from phi to psi. Psi says more. Psi says that phi holds for n consecutive numbers from 0 on. Psi of n means phi of 0 and phi of 1 and phi of 2 and so on up to phi of n minus 1. So I have strengthened phi to psi and applied the weaker principle, our regular mathematical induction principle, to obtain the stronger principle, SIP, for a weaker statement for phi. Is this idea clear?
Yes.
So far, we have got all the three required implications. What is the practical conclusion? Our statements are logically equivalent pairwise. You can take one and logically infer any other one. You can infer any other statement from anyone given among these three. So that means that they are equally usable as axioms. So what is the practical conclusion? After all, our theorem has been proved. The practical conclusion is as follows. One may take anything, either of SIP, MIP, LNP, as the axiom and obtain the other principles as theorems. So you are free to obtain whatever principle. You are free to use whatever principle you like. They are logically equivalent. Any one of them, say MIP, is enough to be taken as a theorem. Is it clear? Probably it sounds abstract. Of course, this result is it has some meta-mathematics flavor. So some reasoning about mathematics, some reasoning about its inner mechanics. Which statement entails which one, which is enough for what? So something like that. The proof here is quite simple, in fact, but it was abstract. So I entirely understand your frustration here. Of course, if you have no prior familiarity with such things, this may seem hard to you, but in fact it is not. Just come back to these things over and over, and at some stage you will see how easy they are. Okay, that's all that I had to tell you about induction. Of course, we shall practice induction later. Induction is one of the central points of mathematics, in fact. But next time we are going to start discussing sets.